Hi everyone. We are going to discuss about ways to fix setup and hold time violations. First of all, we need to know about what is setup time and what is hold time. And later we need to know about what are the reasons for the setup and hold time violations. And finally, we are discussing about what are the ways to fix the setup and hold time violations. Firstly, what are the definitions of the setup and hold time? So the setup time is the minimum amount of time the signal must be stable before the application of the clock signal. So we are applying, we need to have the input must be stable here before certain amount of time from the occurrence of the clock signal. So, and the hold time is the minimum amount of time the data signal should be held steady after the clock event so that the data are reliably sampled. So it is a minimum amount of time the data signal should be held steady after the application of the clock signal. In simply, I'll tell you an example. So for example, a party starts at 7 p.m. and the party ends at 10 p.m. So what do we need to do? We need to come to the party after 7 p.m. or we need to come to the party before 10 p.m. So if we come to the party before 7 p.m., there is no use. If you come to the party after 10 p.m., there is no use. So we need to come to the party before 7 p.m. Sorry, after the 7 p.m. and before the 10 p.m. So it's like the same way. So we need to come to the here before certain amount of time. So which is like 10 p.m. So we need to come to the party before 10 p.m. So it's like a setup time condition. For hold time condition, we need to come to the party after 7 p.m. So it's like a hold time condition. So assume the compare the example with the setup and hold time, so you can clearly understand this concept. So later, what are the setup time and hold time or reasons for the setup time and hold time violations? If the data signal, so consider this is the circuit which is having the two flip flops and the combinational logic which is having certain amount of delay, and these are the two clock signals which are applied at the respective flip flops. If the data launches from the flip flop 1 reaches to the flip flop 2, too long. It's the time taken for the data to come, the time taken by the data to reach to the flip flop 2 is too long. Then we have the setup time violation occurs. It's like the same way. If we come after the, if we come after 10 p.m., we are having some setup time violations. So we need to come before the 10 p.m. in order to avoid the setup time violation. Here, the slack is the new word, which is the difference between the required time minus arrival time. So the required time here is at 10 p.m. and the arrival time here is before the time which is the before the 10 p.m. So here the slack here is the slack here must be positive. So anywhere the slack must be positive. If the slack value is negative, then there is a violation occurs. It may be a setup time violation or a hold time violation. We are going to calculate the slack value for the whole time also, but the formula changes a bit. Let's check the setup time condition graphically. Here is the clock we have applied, and here is the data signal. So after the application of the clock signal, the data signal at the output changes after a certain amount of time. So that certain amount of time is due to the delay from the clock to Q, the clock to Q of the flip flop. So due to the clock to Q delay of the flip flop, the data comes to the output after a certain amount of time. So the data which is here reaches here. The data which is present here reaches to here after a certain amount of time. That time, the time is due to the delay produced by the combinational logic. So after a certain amount of delay, we are having the input to the flip flop 2 here. The input to the flip flop 2 is stable here. So after application of the next clock signal, the data changes. So what do we what is our requirement? We need the data signal to be stable before the application of the clock signal, before the certain time before the application of the clock signal, before the occurrence of the positive sticker. So we need to have stable data signal. before certain amount of time from the occurrence of the clock signal. So here the signal is stable, so we are not going to face any setup time issues. So let's check for the hold time violation. So if the data launcher from the flip-flop 1 reaches too early, if we reach the party too early, there's no use. So here, then we are violating the condition. We are violating the hold. Then the hold time violation occurs. So this is the circuit: flip-flop 1, flip-flop 2, and those in between those two flip-flops, we have the combinational logic circuit, and we have introduced the three buffer circuits here. The clock signal which is applied to the flip-flop 1 is the clock signal reaches to the flip-flop 1 within no time, and the clock signal reaches to the flip-flop 2 after certain amount of time. So because we have introduced the three buffer networks, and let's say we have applied the clock signal at here. This is the clock signal, and the next clock signal is clock B. The occurrence of the clock B signal occurs after certain amount of time. Here this is where the clock B signal applied, and this is the input of the flip-flop D flip-flop. So we have applied the D flip-flop. Due to the delay produced by the clock to Q, the input, the D input changes after certain amount of time. So here is the output of the flip-flop 1. Within the delay produced by this combinational logic is 0. So after within no time, the data gets inverted. So here the data gets inverted, and later after certain amount of time, we have the positive edge trigger. So this after the occurrence of this positive edge trigger, we have the change in the output Q. So this change in output reaches here within no time. Within no time, it reaches here because the delay produced by this combination logic is very low. So whenever we have applied this clock signal, within with the delay of the clock to Q, the input signal gets inverted. So within no time, we have considered this violation with respect to the clock B. So after the occurrence of this clock B, we need to have the stable output for certain amount of time. That certain amount of time is called the hold time. So within no time, the data signal gets changing. So within no time, it's changing. We are coming to the party too early. So if we come to the party before 7 p.m., what's the use? We don't need to come to the party at that time because the party not yet started. So here we are not satisfying the condition. Here the slack formula is arrival time minus required time. The arrival time here is the time at which we are coming, and the required time is the 7 p.m. So we need to come to the party after the 7 p.m. so that the slack value is positive. If the slack value is negative, we are going to face the hold time violation. So now we are going to discuss about the ways to fix the setup and hold time violations. So let's take this circuit, which is having the two flip-flops, a combinational logic, the same as I have discussed earlier. This circuit is having some kind of specifications like what is setup time, hold time, clock period, not net delay, clock to Q delay, combinational logic delay. So we are going to calculate firstly. We are going to check the setup and hold time conditions. From them, we are finding what are the which violation is present, if it is a setup time and it is whether it is a setup time or hold time violation. From that, we can try to rectify those violations by changing the respective values by making some changes to the circuit. So firstly, we need to calculate the setup time. The setup time, it means the signal must reach here before certain amount of time from the occurrence of the positive edge trigger. So it means the signal must reach here before t minus ts seconds. Here t minus ts seconds is 10 minus 2 seconds. 10 minus 2 means 8 nanoseconds. So the signal must reach here before 8 nanoseconds. What is happening here is, if we apply the clock signal here, the data signal which is here present here after 0.5 nanoseconds, because the 0.5 nanoseconds is the delay produced by the combinational logic. So after 0.5 nanoseconds, we are getting the output. What do we need? What we need is we need to have the signal before 8 nanoseconds, but we are getting the signal after 0.5 nanoseconds. It means the condition is satisfying. We need a signal before before 8 nanoseconds. But we are having the output at 0.5 nanoseconds. It means that before 8 nanoseconds means less than 8. It means less than 8 is 0.5 is the less than 8. 0.5 is less than 8, right? So here the setup time condition is satisfied. Let's check for the hold time condition. Hold time means the signal must be stable after the signal must be stable for th seconds. It means hold time seconds. Hold time here is 1 nanoseconds. So if we apply the clock signal here, so the same signal applied here within 0.5 nanoseconds, the signal applies here. What we need to have the signal, the previous value which is here, the previous value present here is stable for 1 nanosecond, but it reaches the signal at 0.5 nanoseconds. We need to have the 1 nanosecond, but it changes at 0.5 nanoseconds. It's a violation. So in this circuit, with this specification, we are facing the hold time violation. So this can be reduced by increasing the combinational logic delay. So let's say we increase the combinational logic delay by 8.5 nanoseconds. So the total combinational logic delay is 9 nanoseconds. So keep in mind that the combinational logic delay is 9 nanoseconds. Let's calculate the setup and hold time conditions. So what do we need to have? We need to have the data signal before 8 nanoseconds. But the combinational logic delay is 9 nanoseconds. So the clock signal which is applied here reaches here after 9 nanoseconds, which is after 8. What we need to have? We need to have the signal which is present before 8 nanoseconds. But we are having the signal at 9. 9 is not less than 8, right? So here we are facing the setup time violation. So let's check for the hold time condition. What we need to have? We need to have the signal to be stable for 1 nanosecond. But we are having the signal after 9 nanoseconds. So after one, we need to have the data signal must not change before 1 nanoseconds. After 1 nanoseconds, we are not having any problem if the signal changes after 1 nanosecond. So the signal changes at 9 nanoseconds. After 1 nanosecond means 9 means after 1, right? So there is no hold violation. Here we are having the hold violation. If we increase the combinational logic delay to the 9. So what we need to do is if the combinational logic delay is 0.5 nanoseconds, we are having setup violation. We don't have any setup violation. We are having the hold violation. If the combinational logic delay is 9 nanoseconds, we are facing the setup violation, but no hold violation. So from this we can see that we can adjust this combinational logic delay so that we can rectify the setup and hold time variations. So that if we decrease the combinational logic delay to, let's say, 8 nanoseconds, for example, if the combinational logic delay is 8 nanoseconds, so the signal reaches to the input of the flip-flop at 8 nanoseconds. What we need to have? We need to have the signal to be present here at 8 or before 8 nanoseconds. So it's the condition is satisfying. For hold time, the signal needs to change after 1 nanosecond, but the signal changes at 8 nanoseconds. After 8 means 8, right? 8 means after 8. Sorry, 8 means after 1. The condition is satisfying. So in order to avoid the setup and hold time violation, the combinational logic delay must present in between the 1 nanosecond and 8 nanoseconds, so that we can avoid the setup and hold time violation. So for these specifications, by adjusting the combinational logic delay to a certain value, we can fix the setup and hold time violation. From the above discussion, I can conclude I have concluded the delay of the combinational path as the minimum combinational logic delay must be greater than the hold time of the flip-flop. Sorry, hold time of the capture flip-flop. And the maximum delay of the combinational path is less than the clock period minus setup time. So from the previous discussion, we have calculated these calculations. We have made these calculations. So for if the time constraint is present, so you can check these. You can check these inequalities, so that if the specifications satisfy these two inequalities, there is no setup and hold time variations. So let's take another example. So these are the specifications here: 6 nanoseconds, 5 nanoseconds, 10 nanoseconds, and 0.5 nanoseconds is the combination logic delay. Let's calculate let's calculate in the same order. We need to have the signal to be present before 10 minus 6. We need to have the signal to be before 4 nanoseconds. 10 minus 6 means 4, right? So we need to have the signal to be more than 4 nanoseconds. But we are having the signal after 0.5 nanoseconds. It means it's satisfying the setup condition. Let's take the whole time as the 5 nanoseconds. So we need the signal to be stable at 5 we need the signal to be stable for 5 nanoseconds after the application of the clock signal. So we need the stable signal for 5 nanoseconds, but at 0.5 nanoseconds the signal is changing. So here the whole time variation occurs. So let's say the combination logic delay is of 5 nanoseconds. Let's increase. Let's change the combination logic delay. As I have said that if there is any violation, just change the delay of the combination logic. So apply the same here. So if the combination logic delay is 5 nanoseconds, let's calculate the same way. The 10 minus 6 means 4 nanoseconds. So before 4 nanoseconds, we need a stable input. But here, because the combination logic delay is 5 nanoseconds, we are getting the stable input after 5 nanoseconds. We need the input to be stable before the 4 nanoseconds, but we are having the combination. Due to the combination logic delay, we are having the input at 5 nanoseconds. So the condition is violating here. So we can say that here we are facing the setup time violation issue, and in the same way we can calculate the whole time also. For the whole time, the signal to be stable for 5 nanoseconds. Here the combination logic delay is 5 nanoseconds. So it is satisfying the whole time violation. So from the above and current specifications, we are not we are facing the both setup and whole time violations. So we are not rectifying those two at a time. So by changing the combination logic delay, we can't able to rectify this issue, because the condition here is, according to the above inequalities, the minimum delay is greater than the 5 nanoseconds, maximum delay less than clock period minus setup time, which is the 10 minus 6 or 4 nanoseconds. The maximum value less than 4 nanoseconds, minimum value greater than 5 nanoseconds, which is impossible to rectify. So we cannot rectify this problem by using changing the combination logic delay. So we can change we can fix these violations by changing the clock period. So this is the solution to this problem. So we can change the clock period. So for example, we can. So how much amount of time we need to? How much amount we need to increase? Here is the amount is setup time minus hold time value, 6 minus 5. We need to increase the value. It may be any value which is greater than 1 nanosecond. So I have written here 6 minus 5 is equal to 1. It is equal to 1. It's not minus 1. It's equal to 1. Sorry for the mistake. Sorry, it's my mistake. So we need to increase the clock period. So the new clock period is 11 nanoseconds. So the combination logic delay now is the combination logic delay is 5 nanoseconds, and the clock period is 11 nanoseconds. So now calculate the setup time and hold time conditions. The setup time condition is 10 minus 6 means 4 nanoseconds. Sorry, the new clock period is 11. 11 minus 6 is 5 nanoseconds. The signal must we need to have the signal to be stable at 5 or before 5 nanoseconds. So with the combination logic delay the 5 nanoseconds, so we are having the output at 5 nanoseconds. So we are not facing any delay issues. In the same way, we can calculate the whole time also. The whole time here is 5 nanoseconds. So we are having the input to change at 5 nanoseconds. So we are not facing any whole time issues. This is the from the above discussions. I have summarized the theory into these three inequalities which are here. The minimum delay must be greater than the whole time of the capture flip-flop. The maximum delay which is less than the combination clock period minus setup time, and the clock period is greater than or equal to setup time or hold time. So if we are given any problem, first of all we need to check this condition: clock period must be greater than or equal to setup time plus hold time. So later we can check we can go for these two inequalities. If the minimum delay is greater than the hold time, there is no hold time violation. If the maximum delay is less than the clock period minus setup time, then there is no setup time violation. So this is the next example. You can calculate the setup time and hold time conditions. I have given this. I have given this to memorize the previous discussions. So in this example, there is no setup and hold time violation. You can calculate the setup and hold time violations orally. So and take the next circuit. This is the next example. The specifications here are the 4 nanoseconds, 3 nanoseconds, 10 nanoseconds, 0 nanoseconds, 0 nanoseconds, 8 nanoseconds. The combination was delay. The change here, the difference between this problem and the previous problem is here we have we can change the combination logic delay in the previous examples, but we are not allowed to change the combination logic delay in this example. So which is fixed. At that time, if the violation occurs, we need to introduce buffers. It's like this. We need to introduce the buffers like this. The buffer which is introduced between the clock and the second capture flip-flop is the T capture. The delay of this buffer is the T capture, and the buffer which is placed between the clock and the flip-flop one is having the delay of the T launch. I'll tell you a tip that if the setup violation occurs, we need to remove the delay elements in the data path. If the hold violation occurs, we need to introduce the delay elements in the clock path. So, you need to introduce the delay elements in the path, in the data path. So these are the tips. For setup time, we need to remove the data delay element. For hold time, we need to keep the delay elements. So this is these are the specifications. For example, let's calculate the setup time condition. 10 minus 4 means 6 nanoseconds. So we need to have the input to be stable before 6 nanoseconds. Here we have the combination logic delay is the 8 nanoseconds. 8 nanoseconds means the input stables after 8 nanoseconds, but we need to have the input must be stable before the 10 minus 4 6 nanoseconds. Here the condition is not satisfying. We are having the setup time violation, and we can calculate the hold time violation also. We have the hold time condition is hold time here is 3 nanoseconds, but the combination logic delay is 8 nanoseconds. But it means we need to have the data signal to change after 3 nanoseconds, but the data signal is changing at 8 nanoseconds. So the condition is satisfied. So we are not going to face any hold time violations. So why all these discussion? Just calculate these inequalities. If you remember these, actually it's better to go conceptually. We can solve any type of circuits. If we use these inequalities everywhere, we can face some issues if you are given a complex circuit. So just go through conceptually. So we need to fix these in order to fix this set of violation. We are going to introduce a buffer. So what I have said is in order to avoid setup violation, we can eliminate the delay elements in the data path. It means we can keep the data elements in the clock path. So for this example, for the sake of this example, let's not consider this T launch. Let's consider this T capture only. So the data is going to capture at flip-flop at the clock after the time at 10 nanoseconds plus T capture, because due to this buffer the time is adding to the 10 nanoseconds. So data should be stable before the 4 nanoseconds. The data should be stable 4 nanoseconds before the clock edge at flip-flop 2, and in the above case the clock edge is T capture plus 10 nanoseconds. So it means the data signal must be stable 4 nanoseconds before the T capture plus 10 nanoseconds. It means T capture plus 6 nanoseconds. Sorry, T capture plus 10 nanoseconds. The data signal must be stable before T capture plus 10 nanoseconds. So by using the above inequalities, 8 nanoseconds less than T capture plus 10 nanoseconds means 4 nanoseconds. So after calculating, T capture must be greater than 2 nanoseconds. So if we keep the buffer which is having the delay greater than 2 nanoseconds, then we can avoid the hold time violation. Sorry, we can avoid the setup time violation. So let's calculate for this the clock value occurs at 10 plus 2 so greater than 2 nanoseconds. let's say it's a 3 nanoseconds. So the T capture value is 3 nanoseconds. So let's calculate the setup time condition. Here the T capture value is the 3 nanoseconds. So here is the 8. T capture means 3 nanoseconds. 3 plus 10, 13. 13 minus 4, 9. So 9 is greater than 8. We have satisfied the setup condition. So here we have rectified the setup time condition, and we can derive the inequalities by using the by keeping the T capture and T launch in the circuit. So in the same way, so for no setup violation, T launch, it means the clock signal must be less than the clock. The delay, the combinational logic delay plus the T launch. Here the data path delay is T launch plus T combination. The data path delay means the data path delay must be less than the clock period plus T capture minus T setup. So by using the same condition as we have discussed, but we are adding the T launch and T capture here. After manipulating TD less than the clock period plus T capture minus T launch minus T setup. For no hold time violation, the clock period plus TD plus T launch, which is greater than the clock period plus T capture plus 2 hold. So after doing some calculation, the TD must be greater than T capture minus T launch plus T hold. Sorry, it's T capture minus T launch. So we need to satisfy these. We need to check these conditions. Let's take another example. We have the setup time 3 nanoseconds, hold time 5 nanoseconds, clock period 10 nanoseconds, and the combination logic delay is 2 nanoseconds. So let's check, first of all, let's check the conditions. We have the clock period must be greater than the setup and hold time violation. Setup and hold time values. So 3 plus 5, 8, which is less than 8 nanoseconds. So 10 greater than 8, which is correct. So there is no clock period violation. So there is no violation. So it means that we can rectify the violation. We can fix the violation if this condition is satisfied. So next, calculate the setup condition. For us, the setup time, in order to for no setup violation, we need to have the TD, the combination logic delay must be less than the clock period plus T capture minus T launch minus T setup. So just calculate this. TD is the 2 nanoseconds, clock period is 10 nanoseconds, plus T capture is, let's take T capture minus T launch as the D. So just consider these T capture minus T launch. Initially keep these values as 0. After keeping these T capture minus T launch, if the condition is satisfied, if the condition is satisfied, we are not required to keep the T capture minus T launch unnecessarily, because it provides it provides other problems. So let's initially take the T capture minus T launch as 0 nanoseconds. So let's calculate this. TD minus TD less than clock period 10 plus 0 plus T setup. T setup means 3 nanoseconds. T clock, sorry, here not the plus, here minus. So 10 minus 3 is 7 nanoseconds. 7 is greater than 2. It means no setup violation. Let's calculate for the hold time violation. Hold time condition. We have the TD, hold time greater, the combination logic delay greater than T capture minus T launch plus T hold, which is 2 nanoseconds. There is no delay in the clock path till now. So initially, as I said that T capture minus T launch is 0. Keep the T capture minus T launch. So here this is not minus, this is equal sign. So keep T capture minus T launch as 0. So by keeping T capture and minus T launch as 0, the combination logic delay TD here is 2 nanoseconds, which is greater than T hold. Here we have T hold is 5 nanoseconds, but 2 greater than 5 is not possible. The inequality is not correct. So keeping the T capture minus T launch in the inequality. So then we have the T capture minus T launch as the T capture minus T launch value is less than minus 3 nanoseconds. So for satisfying the above condition, we have the T capture and T launch value is in such a way that the T capture minus T launch is less than minus 3. The value of the T capture minus T launch must be less than minus 3. So let's assume that T capture value is 0 nanoseconds. T launch value is 4 nanoseconds. So 0 minus 4 is minus 4. So 0 minus 4, minus 3 greater than minus 4, which is correct. So let's calculate the hold time on setup condition by keeping T capture and T capture and T launch as their respective values. For T capture, we keep 0 nanoseconds, T launch, we keep 4 nanoseconds. So T launch plus TD greater than 5 nanoseconds, 4 plus 2 greater than 5 nanoseconds. So no hold variation. Let's calculate for the setup time also. TD less than the clock period minus T capture minus T launch. T capture is 0 minus T launch is 4. Yeah, so yeah, we need to keep minus T setup time. Yeah, minus, so that's why I have written minus 3. 10 minus 4 minus 3, 10 minus 4 minus 3 means 10 minus 7 is 3, 3 greater than 2. So no setup violation. So in this way, we can rectify the setup and hold time violation. Till now, we have discussed the basic concepts of setup and hold time violation. Now we are discussing some basic concepts regarding the setup and hold time violation. First one is reducing the amount of buffering in the path. So by reducing the buffering in the path, it will reduce the cell delay, but increases the white delay. So if we can reduce more cell delay in comparison to the white delay, the effective stage delay decreases. So and then and the next one is the replacing the buffer with two inverters placed farther apart. So as we have seen in the circuit, this is this is the buffer. So this buffer can be replaced with the two inverters. So from this we can clearly see that the transition time is going to decrease. Adding these inverters decreases the transition time. So this decrease in the transition time is due to the decrease in the RC delay, which is the interconnect delay. So by keeping these in two inverters, we can reduce the we can reduce the delay, so that we can reduce the setup violation. As I have said that for avoiding setup time violation, we can decrease. We need to decrease the delay produced by the path. If we decrease the delay produced by the path, we can rectify the setup violation. Next one is the HVT swap. HVT swap means we need to keep the threshold value to the lowest value, to the minimum value, so that the resistance value decreases. So the resistance value decrease in the threshold value decreases the transition time, not the transmission time, sorry. So the low threshold value provides the low transition time. So propagation delay decreases. Next one is increasing the driver strength. Increasing the driver strength means normally larger cells having the higher speed. So if we increase the number of cells, the speed is going to increase. It means that the delay is going to decrease. This is the single stage. If this is a double stage, this is the four stages. These are the 4 stages which are cascaded each other. If this is the let's say the resistance of this network is R. If the two transients are connected in cascade network, the equivalent resistance is R by 2. If the four inverters are cascaded, then the equivalent resistance is R by 4. In this way, we can, as we keep on increasing the size of the transistor, size of the circuit, size of the network, the RC is going to decrease. If the RC is going to decrease, it means the delay is going to decrease. And the next one is inserting the buffers. By keeping the buffers, by keeping the buffer, here it is. Yeah, inserting buffers. Sometimes we insert the buffers to decrease the overall delay in case of the log wise. If we so this can be applicable. We need to keep the buffers whenever we're using the log wise. Inserting buffers decreases the transition time, which decreases the wire delay. So the decreasing the transition time is decreasing the wire delay. So the negative effect here is the area will increases. The buffer occupies the more space as compared to the wire. So the area is going to increase and the power consumption also going to increase. And the next one is sorry, the PPT is not so here the thing. Here the point is inserting the repeaters. So keeping the the concept of the repeaters is same as like the inserting the buffers. For long distance loading means huge RC loading, which is due to the series of RC delays, as shown in the figure. we have these RC networks. The total delay is 9 RC. If we keep the repeaters inside, the total delay is 3 RC plus 2 into gate delay. So the delay is going to the delay is going to decrease. Here the delay is 9 RC, but here the delay is 3 RC plus 2 into gate delay. And the next one is adjusting the cell position in layout. So for example, let's say this is the cell A and this is the cell B. The buffer is for example, the distance between the two buffers is 100 nanometers, 1000 nanometers. Let's say this buffer is at 900 nanometers from the cell A. If we now the wire length is here, this portion wire length is very high. It means the delay produced by this long wire is very high because the long wire produces more delay. So if we keep the buffer to in between those two elements, those two devices, the wire length is going to decrease somehow, so that the transition time is going to decreases. In this way, we can decrease the delay time. We can decrease the delay. And the next one is the clock skew. So by delaying the clock to the endpoint, can relax the timing of the path, but you have to make sure the downstream paths are not critical paths. And the next one is the hold violations. As I have said that for hold violations, we need to increase the delay. So these are the data paths from UFF1, UR4, NAND gate. This is from NAND gate buffer and the OR gate, NAND gate to the flip-flop 3. And the next one and the third path is the flip-flop 2, NAND gate, buffer, OR gate, and the NAND gate. So these are the 3 data paths. In the first data path, in the data path 1, we are having the setup time violation. In the data path 2, we are having the hold time violation. So in order to rectify the hold time violation, we need to increase the delay. So for that, we need to keep the buffers. So we need to keep the buffers in the starting point of here we have some conditions like if the endpoint of the hold violation path has setup violation with respect to some other path, insert the buffer delays nearest to the start point of the hold violation path. And if the start point of the hold violation path has setup violation with respect to some other path, insert the buffer delays nearer to the endpoint of the hold violation path. So else the setup violation increases in other path. So that's why we are for the first condition, we need to keep the buffer in the starting stage. The starting stage to this whole path, this data path is this, but we are not able to we are not allowed to set this buffer here, because it is the meeting point of the setup time violation path and the hold time violation path. So we need to keep these buffer at we need to keep this buffer in between the NAND gate and the OR gate. And the next one is the decreasing the size of the certain cells in the data path. It is better to reduce the cells closer to the captured flip-flop, because there is a less likelihood of affecting other paths and causing new errors. So these are the ways to fix setup and hold time violations. So hope you understand. Thank you.